All right, well, we're going to get started. I'm Ed Swain, the president of the Central Arkansas Astronomical Society. We're based near Little Rock, Arkansas, in a very rural area. We have a 7-acre observatory site, and we usually have meetings there when we can meet in person. But since early this year, of course, we've been meeting by Zoom. On our site, we have several observatories, and we have one remote observatory that people do research through. And a lot of the folks who've used that are really interested in tonight's talk because they've tried to do essentially, scientific work with that instrument. And then we have several folks who do astrophotography from there, and then Bruce McMath does photometry with his. We also have a Dobsonian telescope that's permanently mounted that people can use for visual observation, as well as a refractor in a roll-off roof. So that's where we meet when we meet, and when we go out, people have been observing from that site. Otherwise, we have presentations once a month from members and guests on topics ranging from what we call the dead astronomer presentations to constellation
the almost dead astronomers.
Yeah. And then, of course, on scientific subjects and other subjects of interest to the membership. And speaking of membership, while we've not been able to meet, we've grown to a larger size than our club has ever been before. We're at about 85 members now. Michael Borelli is our membership chair, and he's constantly welcoming new members to the club, and also trying to figure out what those members are interested in and what they expect from the club, because we know not everybody's an observer. We had a discussion a little earlier in our board meeting that not everybody comes out to the observatory. So we're always interested in finding out what our members want from the club. I want to give a real short report. We just had a board meeting before this meeting started, and besides doing ordinary business like deciding on our budget for the next year, we talked a lot about how we make sure that we include members in the leadership of our club, how we make it more open when we have now 85 members versus 40 to 50 members. And we decided we should add some slots to our board to get more people involved and try to get more newer members involved in club business. So that's kind of where we're headed with our club, trying to make sure that we provide the things that people expect. So we have the opportunity with these remote meetings now to involve people from around the country in our club meetings. And tonight we have Bill Hartkopf, who is nationally known, probably internationally known, for the subject he's going to speak about. Bill earned his PhD at the University of Illinois and was a research astronomer at the Center for High Angular Resolution Astronomy at Georgia State University from 1981 to 1999. Then was an astronomer at the astronomy department at the U.S. Naval Observatory in Washington, D.C. I think that's where the vice president lives, is on the grounds of the
He's
Naval
our tenant,
Observatory.
yes.
That's amazing to me. So it makes it difficult if you're in Washington. If you just want to go look at the refractor, you got to sign up months ahead of time to try to get in there to see that. He was at the Naval Observatory from 1999 to 2018, and then retired to Venice, Florida in 2018. Still does part-time contract work for the Naval Observatory. So I'll turn it over to you, Bill, and we'll probably have a few technical issues as we probably bring your screen up with slides, but
I'm sure
we're used to working that out. So welcome, and thank you for being willing to present. And we have guests from around the country as well, so we're glad to have you all with us. Thank you.
Thanks. Yes, I've never given a Zoom talk. I did one remote talk, but I was in Maryland. The audience was in Hawaii, and I had to speak over the phone and tell somebody next slide, and it was a little bit awkward. We'll see how this works with this. So anyway, I'm going to be talking about speckle interferometry, which is actually the technique's 50 years old this year. And it really revolutionized the way that observers studied visual binaries, resolved binaries, but it's still not very well known. And I figured since I was involved in speckle for most of those 50 years, I figure I should talk about it while I still remembered it, at least the old stuff. And so I'm going to see if I can get my presentation up here. I need to find, there's the share screen. And there's that. See if it's actually going to work. Where'd it go? Okay. Can you see my field now?
Yes.
Okay,
Yes.
good. Because it popped up a little different than I expected it to. So let's hit this. Okay. If you can see that and hear me, then I guess we're good to go.
We're in business.
Okay, great. Okay, so there's the title, of course, 50 Years of Speckle, which makes me feel extremely old. But I'm going to start with a bit of background, the once upon a time stuff here. It's way back in the spring of 1981. I was a grad student at the University of Illinois, and we had a speaker come in who was this young astronomy professor from Georgia State University named Hal McAllister. And there's Hal in a somewhat less formal photo of him I took at his house. He was involved, he talked about this technique of speckle interferometry, which was this kind of not known technique for studying visual binaries. And he gave the background of it. I should start with a little bit of history. The technique had been discovered in about 1970 by this French astronomer named Antoine Laborie, who, very clever guy, I should say, who invented the technique, did a few papers on it. There's his first one from 1970, and made a handful of observations essentially to show the technique worked. But he was this sort of a big idea man, and so he showed it worked, then went on to completely different things and did nothing more with the technique at all. So a few years later, about 1975, some astronomers at Kitt Peak Observatory in Tucson built a speckle camera, and then they hired a postdoc, Hal McAllister, to see what he could do with it. So Hal's idea, there's Hal again, he decided that right now at this point, speckle was just this interesting experiment. Hal decided that if he wanted to change it from being an experiment to a real observing technique, a standard technique, the way to do this was to make lots of observations, very careful observations, calibrate things very well, discover binaries that couldn't be found by other techniques, and then just demonstrate to the binary star world that this did work well. And so he did this as a postdoc, and then after he was hired at Georgia State University as a professor, or assistant professor probably, he kept up the technique and decided to expand upon it. So the timing, I should say, of this talk was perfect for me. It's nice to be in the right spot at the right time, because I was just finishing up my degree and looking for a job. Georgia State wanted to keep him, so they came up with some money to hire an assistant just to reduce data for him. So I applied for it, got it, and later that year I wound up moving to Atlanta and was able to parlay that 2-year temporary position into 18 years at Georgia State as a professor and everything, and then another similar amount of time at the Naval Observatory in the same technique. So worked out well for me. Also, the perfect timing was that 2 weeks after I arrived in Atlanta, this young woman also arrived in Atlanta and started working at the same department that I was in. And before you knew it, that happened. So, so a perk of the job. But as you say, I'm getting off topic. I can hear you. So tell you about speckle. All right. So what do astronomers want? Observers, I should say. Visual observers, the real kind of observers. You want to see faint stuff, right? So easy. You go to a faint site, a dark site, get a big telescope, bigger light bucket, collect more photons, you see the faint stuff. Easy, right? Expensive, but easy. Okay, what else do we want? We want to see lots of details. You want to see the surfaces of planets. You want to be able to resolve very close double stars. So easy as well, get a bigger telescope. Double the size of the telescope, you double the resolution, which means you see things that are half the separation. You see the closer stuff. Well, in reality, that's not quite the case, because while this is good in theory, if you got an atmosphere to look through, well, it makes some differences. And so it's not that easy. So here's the hand waving, which you can't see too well over Zoom. So let's start by sort of picturing a pot of water on a rolling boil. Think of a really big pot, heat sources underneath, and you see the rolling boil. The atmosphere, it's a little bit simplified here, but the atmosphere is essentially has the same kind of convective motion. Warm surface air rises up, cools off, and then kind of flows back down in a fountain kind of thing. And these turbulent cells, which are typically in the 10 to 20 centimeter diameter size, are what really defines the seeing of your telescope. So anything more than the size of the turbulent cells, you know, it doesn't make any difference. You're restricted to about that size. And if you think about it, having a large telescope, say, let's talk about a 4-meter telescope, you may be looking through dozens or hundreds of these convective cells. So imagine starlight coming down through these cells. You can see my mouse, right? So light's coming down through these cells. Causes various tilts, delays in the wavefronts and such. The light comes down, it's interacting with each other, adding, you know, constructive and destructive. And you wind up with this pattern, which you see on the right here, of many, many images of your star rather than a single one if you didn't have an atmosphere to deal with. So these little bright dots are what we call speckles. So I have, now I'll warn you on this, about 1 time in 3 when I run this, it kills my PowerPoint. So we'll see if this does it. It's only like a 3-second video of speckles. So this is a 1 arcsecond binary, and you can see how the image is all broken up, and also how they dance together. Maybe. There we go. So you can see they dance very well together, and it didn't kill the screen too. That's wonderful. Okay. So you got that. So how did Laborie get, you know, measurements from all that dancing stuff? First off, we got to collect the data, and then I'll show you how to do that. This was the Kit Peak speckle camera from 1975. So this is before the era of lots of very good CCDs and such. This was a film camera. So, and this is Roger Linds, who was one of the people who built it. Now, where he's located right now, he's sitting in the Cassegrain cage of the 4-meter. So right up here, above him, is the main mirror for the 4-meter, and the Cassegrain hole is right here, so it's attached there. So light comes down here. There's an image intensifier. Because the atmosphere moves very quickly, you have to take very rapid snapshots to freeze the atmosphere. So if you think of film, which is not all that sensitive, taking very rapid snapshots, and you've also blown up this image hugely, you know, it's not very sensitive. So you need to have something which, you know, intensifies the image. And then there's all sorts of other optics there to, you know, filters and something to compensate for atmospheric dispersion and all sort of stuff. So it comes down here to take images on film. So the camera was set up so that it could take 100-foot rolls of Tri-X black and white film. So the person here in the cage would talk over an intercom to the telescope operator. He'd say, move to this star, and then he'd hang on. And as he's lying on these little bits of foam and such, as the telescope swings around and him with it to his first object, then he kind of orient himself so he could look through the eyepiece, center up the star in this 2 or 3 arcsecond field, and then guide on it while he took 50 to 100 snapshots of the star he was looking at. Then he'd repeat that maybe 100 times over the course of a night, you know, to get all his data, and had lots of rolls of film to develop afterwards. Now, fortunately or unfortunately, let me take a little water here. I arrived at Georgia State just after the last of these photographic runs was done. So I never got the experience riding around in the back of the telescope and being, bounced around like, a pinball machine or something like that all night. But I did overlap with one of Hal's graduate students, a woman named Elaine Hendry, who did a fair bit of this observing. Now, if you know most graduate students and postdocs and things, they tend to dress, let's say, casually, jeans, t-shirts, sweatshirts, that sort of stuff. Elaine was a little different. She always dressed in dress and high heels all the time. Whenever she came to the office, whatever, even on planes, traveling to different locations. She'd have, of course, her observing clothes here, ratty clothes for riding around there. But unfortunately, one time her luggage did not make it to Arizona when she did. So, and you can't sort of postpone your observing time. So she wound up riding around in the back of the cast cage for 1 or 2 nights and trying to observe in dress and high heels. So, which had to have been an interesting experience. I'm sure it's completely coincidental, but she later married the telescope operator. So I have no idea what that, had absolutely nothing to do with this, I'm sure. So, okay, anyway. So now you've got lots of film. So here's just a sample of some of this film. There's lots of it. Now we need positives. We can't use negatives to do our reductions, which as you'll see in a moment. So this all has to be converted to positive film. And that's kind of hard to do. So Hal found out he could splice all these rolls of Tri-X film and put them on a big movie reel. And then he would ship it off to a film lab, which turned out to be in Hollywood, which was set up for making positive prints of films. So at this time, which was, late 70s, there wasn't a lot of use of black and white film. And it turns out this film lab had only one other job in black and white, and that was making new copies of I Love Lucy reruns. So we have an interesting connection with Hollywood, don't we? So, okay, we make negatives, or positives, I should say. So we got a whole pile of these, thousands and thousands of these. So how do you reduce this stuff? That's an old friend, which you may have learned about in high school science, freshman physics, whatever, of Young's double slit experiment. So imagine, here's wave fronts, either water waves, light waves, whatever, and it comes to a wall with a couple of little slits or openings in it, apertures, and you've all seen this sort of thing with waves kind of coming out, interfering with each other. Of course, the crests of waves adding with crests of waves make something twice as high, crests meeting troughs and canceling each other out, all the rest of it. And on the far wall here, you wind up with a fringe pattern of bright spots and dark spots. And the separation of those fringes depends on the separation of the apertures here, or the slits. And this is the technique that Labrie figured out could reduce this data for him. So let me get back to a single frame. This is a real wide pair. I did that so we can kind of see them a little more easily. So imagine you have a laser that shoots through the whole thing. You broaden the beam of the laser and shoots through the whole thing to a distant wall. And each of these pairs of speckles is like 2 apertures of Young's double slit experiment. So, this one over here and this one over here makes a set of fringes on your far wall, and this one up here and this one down there does the same thing. And so all these various random positions of apertures form fringe patterns, which essentially cancel each other out. They're going all different directions, all different widths, and you again get smeared out into nothing, or just a seeing disk or something like that. However, Labrie, being very clever, realized that, okay, if you got, say, this speckle here and this speckle here from the double star, is going to give a fringe pattern, and this speckle here and this speckle here is going to give the exact same fringe pattern because it's the same separation and angle, and every pair of corresponding speckles from your binary star are going to give the same fringe pattern. So that's going to add on top of each other, and they're going to not cancel each other out, but you'll have big, broad fringes or very sharp fringes from them, and the rest of it's going to be all washed out. And those are some early results of this. 12 Persei, which I think was a pair that Hal first resolved. McAllister 8, if I remember, forms this fringe pattern. This one, a much wider binary, quarter of an arc second, it's a wide one, gives much sharper fringes or closer fringes. So you can either measure the separation of those fringes, and with scaling you figure out what the separation of the binary star is, or you could shine a laser beam through this as well and wind up with two little dots again. You're sort of doing the full autocorrelation by running through a laser again. So with this, Hal's able to make lots of observations. With photographic technique, he could get down to, he could do the bright star catalog. He'd get down to maybe 6th magnitude, but with film and all, that's about as faint as you could get with it. So now I said that you needed to make lots of observations, but you also needed to make them well calibrated so they're useful. So this is an example of how we would do calibration. This people might be able to recognize is the Mount Wilson 100-inch telescope. And up here at the front end of it, they're installing a slit mask, a double slit mask. There's little metal frame, box frame to form the slits, which fit into registration pins so that it's very well defined where it is. And then canvas and Velcro covers up the rest of it. So you have a double slit there. You look at a very bright star and you make an artificial binary out of this. And the separation on your photograph or whatever of the double star depends only on this separation of the slits, which you know, and your wavelength. So you can do an absolute calibration and get extremely good results for the double stars by using calibration like this. There was a similar thing for the 4 meter, though putting a 4 meter wide mask on top of it was not practical. They had some other techniques which got a little more complicated, but same overall idea. Okay, as I say, I missed out on the photographic observations. I did do a lot of photographic reductions, but at the time I was getting there, they were just designing an electronic version. So, and here it is mounted on the 72-inch telescope out of Lowell Observatory. So this is Hal and me and Otto Franz of Lowell Observatory, who I believe is in his 90s now and is still alive and crusty as ever. So this by the electronic cameras, we didn't have to ride around in the cage anymore. We could do it remotely from the observing room, which was much easier. We didn't have to develop the film and all that. We had obviously different techniques than using lasers to reduce our data, but the overall idea was the same, except you're doing it on a computer instead. And one example of a method of doing this reduction, you're actually seeing this being done in real time here. This is some infrared data on the left from the 6 meter, the old Soviet 6 meter telescope. And it's being reduced by this bispectrum analysis technique. And you can see the double star. You look at this and you say, there's no chance there's a double star in there, but obviously it's coming up here and you can kind of see the magnitude difference between the two of them quite easily. So different techniques like this have been used to reduce data ever since we switched to these electronic things. Now, as I say, with the electronic cameras, we started with the earliest CCDs in 1981 and 82, and those have gotten better and better over the years, much more sensitive. So what was at the beginning maybe a gain of 2 or 3 magnitudes over photographic went to quite a few more magnitudes. We can probably get to 14th, 15th magnitude, and the newest ones are getting larger and larger magnitude differences too, so we can get much fainter secondaries than we could before, which is great because the photographic was limited to 2.5 or 3 magnitudes. It was about as much of a difference as you could get and dig it out. So a nice thing about the speckle camera, especially with the electronic ones, They went much smaller and more compact, which meant you can take them all over the place. So the Kitt Peak camera, or the Georgia State camera, and the USNO cameras went to many different places. We did a lot of observing at Certalolo in the southern hemisphere. We did McDonald Observatory, Lowell, as I say, and let's see, the 4 meter and the 2.1 meters at Kitt Peak, and, you know, all over the place. Got lots of observations. Oh, this one, by the way, here, that shows the cage at the bottom of the 4 meter that you're riding around like a, you know, gumball. You know, must have been fun. Now, these are all kind of big telescopes, but actually a lot of the observations we did, especially at USNO, was using something a little bit smaller. This is the 26-inch Clark refractor from 1873. This was the largest telescope in the world when it was built, and this is the telescope that the moons of Mars were discovered with in 1877. This telescope has also made more double star observations than any other telescope in the world. It's made something like 55,000 observations of double stars so far, but photographic, filar micrometers, and 30,000 plus measures by speckle since we started the program there. So it works really well. The telescope is now under computer control and has the latest version of cameras just being software developed, I think, right now. So it's a lot of changes even the couple years since I've left. Now, to show you that even a small telescope, which obviously doesn't have the resolution of a 4 meter, it can still do stars that really can see over your lifetime that move. So here's an observation of one. Sort of ignore this central spike here and think of these as the 2 double stars. And you can see over the course of a few years, you know, we can see actually a few stars move around. Most of the stars we observe with it are too wide and too slow moving, but you had to find one which you say is a typical example, right? Okay, so what's good about speckle interferometry? What are its advantages over the other older techniques? For one thing, as I've mentioned, we can get much closer pairs because this light coming down through these different patches of atmosphere are interfering with each other over the whole width of the telescope. You actually reach the resolution limit of that telescope. For a 4 meter telescope, that's about 30 to 35 milliarc seconds, so 300ths of an arc second or thereabouts. So with the 4 meter, we were able to make enough observations of Capella, which is about a 55 milliarc second pair, to do you know, a quite good orbit for this extremely close pair. They're both, you know, a little bit brighter than first magnitude. The 2 stars are separated. I looked it up. They're about the separation between the Sun and Venus, I believe, in physically. This pair actually was observed with out at Mount Wilson in 1919 with a 20-foot beam interferometer that was put on the end of the 100-inch. Made good observations as well. And because this is a 100-day period and it's been observed something like 400 orbits at this point, we know the period of Capella down to a couple seconds of time, despite being a 100-day period, which is probably one of the best known orbital periods that exist. So, and yes, we did observe a 0th magnitude star with a 4 meter telescope, which is an interesting thing to do. So you observe close things, and also you can observe well. You can observe with high accuracy. This is a kind of a long known system, Eta Corbohr, and these little green dots here, these little plus signs are visual observations of it over the course of probably a century and a half here. The lines connect the observation with where its predicted location is on the orbit. So you can see there's lots of them, some of them a little bit better than others, as you can tell. The blue dots here are all speckle observations. And you can kind of see that much better accuracy, which means we can get the orbital elements to much higher precision, much higher accuracy, I should say, which is good for everything else we want to do with them later on. So, okay, so it does close stuff well, and it does wider stuff well as well. We actually have, since there's that high precision there, we can actually look for invisible pairs, ones you can't see, but just their gravitational influence. We can detect the wobble in the motion of something. This is actually a really wide pair, but I got it just because it's easy to demonstrate. As the star is moving down here, you can see the center of mass is wobbling back and forth from the motion of the secondary, which is going around time, and this happens to be the secondary. We actually were able to do that with speckle with other binary stars. In fact, I was able to discover I think a 3 milliarc second binary as a wobble in an orbit of one wider binary, which was simultaneously discovered as a wobble in a spectroscopic binary given the same period. So that really worked out. We were able to figure out all sorts of information about this invisible star this way. Actually, when we figured out we could do this, we tried, unsuccessfully I should note, to observe about 60 stars, 60 binaries over and over and over again to look for wobbles that might be due to planets back in the 1980s. You'd have heard about it if we found anything. We did not. Okay. I don't think I need to go through this in any great detail, but speckle is good at simple stuff, binary stars and things. It's fast, which you'll see in a couple examples I give, which is very useful, and we can make lots of observations. As you can say, we can go pretty faint, and we're getting better than that. Quite accurate. As I say, we're getting better and better on magnitudes. And because we look at a very small field of view, that allows us to work in downtown Washington and make observations of binary stars, because you wouldn't tend to think of downtown Washington, 2 miles from the mall, as the place to do, astronomy of any kind. But we actually still keep that 140-year-old telescope working on every clear night because we can do it with techniques like this. The equipment is, I say, relatively inexpensive, and it's portable, so we can go all over the place with it. Very useful that way. Now, it's not the be-all and end-all, obviously. Complex things, I say, something with a lot of structure to it, it just does not work out. You can't deconvolve all that stuff with speckle. The techniques so far with intensified CCDs and things did not lend itself to very good photometry. The latest versions of CCDs, EM-CCDs and such, are much better in that regard. So we're thinking that second one, that should be able to go away eventually. Extremely large delta M systems, magnitude difference systems, we can't do that either. You need real adaptive optics or something like that to do that. Speckle sometimes is called the poor man's adaptive optics because it doesn't cost so much money and we can build it. It's actually one of our former grad students who now works at the Mount Wilson. He actually wrote a paper for Sky and Telescope on amateur speckle interferometry, so that it can actually, it's within the realm that a well-heeled amateur anyway could build their own speckle camera and be able to do that. So now there are lots of different projects that speckle has been used for, but I just wanted to give a couple brief examples. So, and you can and I can answer questions about any of this stuff, of course. The first example, which was the reason that what Hal McAllister first sort of tackled, was the idea of getting stellar masses. As you probably most of you know, the mass of a star is kind of the most important thing to know about a star. I mean, it tells you how hot the star is, how big it is, what its lifetime is, how long it's going to live. It'll tell you where the habitable zones are of planets around it, and by its length of its lifetime, whether there's maybe time for life to develop around stars. You get all sorts of things like this. So mass is kind of the thing that people want to get. Well, astronomers want to get, the rest of the people don't care, right? And getting masses, if you remember Kepler's laws, masses are just related to the orbital period and the separation between them, the semi-major axis of the orbits you calculate. So by getting good orbits and good orbital elements, you can derive the masses of stars as well. And double stars are essentially the only way we have of figuring out the masses of stars. So it was a good selling point. So Hal tried that early on and had actually some good success with it. Now, if anybody's ever done an orbit of a binary star, you find out that one technique, observing, say, visual binaries or resolved binaries like we're doing here, does not give you all the information you need to be able to figure out masses. You get all the orbital elements, the period and the semi-major axis, the inclinations and all the rest of that sort of stuff. But the inclination, because you're just doing angular separations, is just in arc seconds. And you need it in something real, kilometers, astronomical units, to be able to get anything out of it. You can also observe stars, some stars spectroscopically. If you look at the spectrum of stars, and you see the Doppler shifts, that the spectra go back and forth as they kind of come toward you and go away from you through the Doppler effect. So you can do spectroscopic binaries by studying these motions of the spectral lines back and forth. And that gives you essentially everything, except a spectroscopic binary can't tell you how the binary orbit is inclined in the sky. So you wind up with A, but it has a sine inclination attached to it. Still not enough information to get masses. But if you're lucky and you get a binary which is, you can resolve it, so you can do speckle or whatever, and you can see its spectral lines move. So if it's both a visual and spectroscopic binary, then you got it made. Then you can get all the elements, you can figure out the masses, and the distance even of the binary star falls out. So you're good to go. Unfortunately, there aren't too many stars that fall in that regime. Spectroscopic binaries, they have to be fast enough moving so that their Doppler shifts become measurable. If it's a really slow moving system, the shifts are not going to be noticeable. That means you would, at short periods, close separation pairs. Visual regime, trying to see the two stars, well, obviously they need to be wide enough so you can see them, which means they're wide, they're long periods, which is just sort of the opposite. So historically, there have been very few that sort of overlapped between these two regimes of binary stars. Speckle, when it came in, and suddenly you could get these really closer binaries, it moved into that spectroscopic regime considerably. In fact, that's why some of his very first stars were a whole bunch of spectroscopic, longer period spectroscopic binaries that he could hope to resolve and get masses right away. So, some good stuff you could write up, right at the very beginning to tell people, see, Speckle's doing good stuff. At the same time, fortunately, the techniques for doing spectroscopic work have gotten much, much better, especially in the searches for planets, extrasolar planets and such. So they can get much smaller Doppler shifts, so they can get into the wider pairs regime. So the two regimes are sort of coming at each other and overlapping more and more, which means we're getting a lot more masses, which is great for the field. Of course, with long period binaries, you're talking decades before you get all this sort of stuff. So that's why, some of us work in the same field for a long, 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 long time. Okay, so that masses is one of them. The other example is just various surveys for duplicity of stars. And as I say, speckle was great in that regard because we could do lots of observations. I think our record was, with the 4 meter, was 350 objects in one night, which meant we were working from the time the sun went down until it was peaking above the horizon. And the telescope operator wanted to beat the previous record that a colleague had done, so they kind of were pushing us when we wanted to go to bed. So it worked well. So the idea of how many stars are double stars, triple stars, quadruple, and more elaborate, are an interesting test for anybody who wants to do computer models of star formation. You know, they take a cloud of gas, run their models, and come up with stars. The results they then check and see, okay, how many double stars formed and how many of these, you know, more complicated multiples formed. Does this match reality? And so it's a nice check on models to see how that sort of stuff worked, and for the galaxy as well. I have a couple examples of some duplicity surveys we did. One thing we did we looked at well over 3,000 solar type stars, G stars, and figured out how many of them were doubles. And we also had some other information which could be used as a marker for the ages of the stars. So we looked at the duplicity of these things, you know, after we got all these thousands of them and put it all together, and we found that young stars here were much more likely. This is like 15 or 16% of them were in double stars or triple stars or whatever's. And as stars got older and older, a much smaller percentage, is only a few percent, were doubles for the very oldest of the G stars. So that's an interesting bit of data for anybody doing modeling as well. What we think is actually happening is that, of course, G stars, they last quite a long time. As the stars are orbiting around in the galaxy over time, they're not just orbiting, you know, around this way, but they're also kind of dipping up and down through the plane of the galaxy. So we think, we're not sure, but we think that as the stars are going down through the plane of the galaxy, the density of stars is much higher in the plane, the disk of the galaxy, and there's more chances for interactions, which might be causing some of these binaries to rip apart. So as you expect, the more orbital revolutions of the galaxy these guys make, the more the likelihood that some of them get stripped of their companions. So we think that's what's going on there, but it's not certain yet. The other survey we did, or an other survey we did, was we looked at all of the O stars, the hottest, you know, most massive stars. We looked at all of them fainter than or brighter than 8.5 or 9th magnitude. So all skies survey of everything. And we found that that these hot massive stars were very likely to be in double stars and triple stars and such, as opposed to less massive stars, which was kind of an interesting finding in itself. Also, you know, massive stars don't live very long, so they tend to be formed in clusters or little associations of hot stars, you know, big clouds of gas. And because they don't live very long, most of them kind of live their entire life in that cluster. They don't have time to move out of the cluster before they, you know, blow up or whatever. So the stars that are in the clusters turn out to be much more likely to be double stars than the hot stars that have escaped and are off in the field. There are virtually none of them that are just by themselves out there are doubles or multiples. They're all single stars, whereas the ones in the clusters are very likely to be doubles and such. We think what's going on there, in fact, we have one example, is that there are interactions because it's a tight cluster, and you imagine two double stars that are coming together, that they could have a gravitational interaction which causes some stars to be ripped off and ejected. And here is an example. This is Orion. Here's the trapezium in here. And observers found this star, Mu Columbae, going that way. Whoops, whoop, back it up. Very rapidly. This one in Origi was going this way very rapidly. And if you trace the movie back to, you know, in time, especially as they got better and better proper motions, they found they both wound up in the trapezium at the same time. So we think those two double stars did a close encounter with maybe another pair, which works out for the angular momentums and such. And they just, two of them got shot off in two different directions at extremely high speed. So these are called runaway stars. So we think that might be the reason, or a reason, why these hot stars off in the field are single, whereas the guys in the clusters tend to be multiple stars. So Lots of other surveys we've done as well. We surveyed about a third of the bright star catalog, so about 3,000 bright stars, and all sorts of other types of classes of binaries and such. So it's still an ongoing thing. It's gotten to be more difficult to get telescope time on the big telescopes. So that's why, in fact, at USNL, the vast majority of our observing is done with the 26-inch, which has its limitations, obviously, because it can only get down to quarter arc second, 2/10 of an arc second separation or thereabouts. But still does a lot of good stuff on neglected binary stars. And we're trying to get some other collaborations and things, because there are some other groups in the world that do this as well. So there's still, I think, a big future for this ancient technique of speckle. I probably won't be doing too much more of it because I'm ancient myself, but you know, it's something open for lots of you youngsters out there. And that is it. And let's see if I figure out how to actually stop share. I guess that's how this works. Bing, it stopped. Oh, there you all are. I could see one of you this entire talk. So, anyway, I'll be happy to talk about, answer any questions on some of this stuff. I sort of went through it actually a little bit more rapidly than I thought it would. But if anybody's got questions about any of it, I can wave my hands and point you at somebody else to do the work. I'm pointing at Rachel. I'm not quite sure if that works. So anyway,
so Bill,
yeah.
I got a quick question.
Hello, Michael. Old roommate,
hey,
by the way.
Old roommate. He was one of my groomsmen too, an office mate.
And we've been to 2 solar eclipses together, and
Yes.
Shooting for number 3 in a few years too.
Yeah, coming to Arkansas.
Right.
So here we go. You were talking about the G stars because of their longevity. They could have been started out as double stars,
Mm-hmm.
and then got ripped apart by gravitational interactions off the mid-plane.
Right. Now you should remember that.
Over what time of period? I mean, could that have been like this for over what period? A time of period? Could, for example, could the sun have been an initial double and then lost a partner?
That's hard to say. Well, the orbital period for the galaxy is what, 250 million years? Is that about right, Rachel? So,
yeah.
So that's the sort of time frame we're talking about. So these stars could have gone through the plane, you know, numerous times. Whether the sun did, well, that I have not sure we can tell about that. For a long time, there was this discussion of that stars could either have planets or be in doubles, but not both, and that has sort of been pretty well disproven by this point. So, but whether the sun could have had a companion, or whether it still has that mythical companion out there, that I'm afraid I can't answer. Oh, there's Russ too. Wow.
Oh, a question for you, Bill. The number of us are kind of working on this, what you could call quasi-speckle of some sort, where we make integrations that are longer than speckle, so we're getting some smearing, but we're doing, you know, a single star observation for deconvolution. Then we're using bispectrum analysis, and it seems to work out better than stacking or lucky imaging.
Right, I understand it did, yes.
And so are other people kind of doing that, or is yeah, any thoughts on it?
I'm a bit out of the field now, of course, since I've been, you know, I'm a retired old guy at this point, unlike you youngsters, Russ. So I don't know of any other groups right now that are involved in that. I don't know if there's a French group, Loss, Florent. Is he involved in that? I don't recall offhand.
Yeah,
but you'd have to check with the youngsters.
Okay, got it.
Yeah.
First off, thank you for the talk, and thank you for Michael for setting this up. I guess he was the instigator.
Yeah, he twisted my arm over the internet.
Yeah, so I've looked at on YouTube, and I've seen one fellow that did some work with like a 12-inch telescope. So I guess I'm kind of interested in defining the boundary This guy put up the basically he was limited by the magnitude, by the dark sky that he could get.
Well,
you can't beat that. And then the other thing is you've mentioned it too, the resolution of the scope.
Right. Well, with our 26-inch in downtown, we were able to reach. We were getting some 13th and 14th magnitude stars from downtown Washington. So because you're looking at such a small field of view, that helps you a lot in the background light situation.
Yeah, okay. So, but it's still there. I mean, at some point you got to hit the wall. You don't get enough photons over the background.
Yeah, it's right. It's more the sensitivity, I think, of the detectors. And in fact, I'll be interested to hear how this newest detector they have, how much better it can do. Okay.
Mm-hmm.
But it's probably getting toward the limits. But then there are a hell of a lot of stars down to 12th magnitude, which should be obtainable, that one can observe.
What is the separation? I mean, what are the constraints on the separation of the things? And the reason I'm asking is because Bruce and I are launching on CCD, and I'm trying to see how close I can push just, mapping the star's position at subpixel accuracy. And, we're getting down to a few pixels, and yet how is that is there going to be a gap between these methods, or do they overlap, or you have any notion or just thoughts?
With the speckle camera at the observatory, or at the Naval Observatory, true speckle, you have to be closer than a few arc seconds, which is the size of this isoclinetic patch, or the turbulent cell size. We do much wider stars there, which is this sort of quasi speckle that Russ was mentioning. It's not true speckle, and light isn't going through the same patches of sky, the light from the two stars all the time. But using the reduction techniques, we can still get pretty good astrometry out of them, even though they're not really in the speckle range. So that kind of bridges this gap between what are true speckle regime and the visual regime. So we've gotten some pairs out close to an arc minute, actually, with the 26-inch, with just use different microscope objectives to get different ranges. So we can easily bridge that gap. And I'm sure Russ does that sort of thing. I don't know how close Russ's telescopes, what size telescopes you mostly using, Russ?
Yeah, so we've got an 11-inch. It's a C11 optics, and we've tried different magnifications, and we can go down to 1 arc second, a little bit below 1 arc second separation with 11-inch, and we've gotten down to 13th magnitude. So you can do a lot with an 11-inch telescope. And Ryan Caputo, one of the students, he's used a 6-inch telescope with good results down to about 2 arc seconds. And but the trick is you do have to have the right plate scale. So you often have to add a Barlow in your optical path to magnify this. We use a 1.5x Barlow here.
Russell, are you, this is Bruce, are you using speckle technique that you're talking about now?
We use speckle on the, if they aren't too faint, we'll use speckle with, typical exposure times 40, 50 milliarc seconds. But we've been experimenting on, and we can do that down to like magnitude. But we've been experimenting on 13th and even a little fainter with longer integration times, which smears the speckles out, but it doesn't. You don't totally lose the high frequency information, and so the deconvolution star and the bispectrum analysis still pulls the stuff out quite nicely.
I should say Russ is also interested in doing automated speckle, setting a telescope. Like he was actually one of the pioneers, making me feel old, in automated photometry telescopes back in the, I don't know, 18th century or something like that, right, Russ? But he's experimenting with trying to do automated speckle as well, give it a list of stars to observe and have it run and do speckle on a whole bunch of them, and then just spit out the data at the end of the night, I guess.
Yeah, we're making good progress on it. So the main participant, the main person working on this is Dave Rowe, who's the chief technical officer at Planewave Instruments. And we're using my little 11-inch telescope here as a test bed. But the goal is to, we're already lining up a 1 meter Planewave telescope in Chile, one up in Michigan, and one up at the Sierra Remote Observatory, a 17-inch. So we hope to, once we get the automation working, then to have a number of 0.5 meter to 1 meter telescopes that can do this automated. So I wrote down your 35,000 speckles at the Naval Observatory. So I don't know how long.
That's your goal to beat, right?
Yeah,
I see. Yeah. Yeah, when they passed our Chara numbers, some years ago, I sort of felt proud and sad at the same time, I guess. But that's what it is.
So I'm curious from viewed from the perspective of a rank amateur, and how you would go about defining a list of stars that would be useful to observe, whatever technique you're using.
Yeah, Bruce, I can, let me answer it quickly. So Dave Rowe again, what he did is he downloaded the entire Gaia DR2 database and searched for double stars on it. Found like 6 million of them. And so that's a raw database. And he developed a tool called Gaia Double Star that we use, so you can set parameters, how faint you want to go, what RA and deck you want to do, the separation that you want to look at, and it'll spit out all sorts of candidates to observe. We've updated it recently. I was interested in doubles that are moving fairly quickly, have short periods, so we can see a little action, if you will. And so I just came up with a simple equations to convert Gaia parameters into rough estimates of orbital periods. And we checked it against the 6 orbit catalog, against known by, and it does a fair job. It's of course not perfect because it kind of assumes, circular orbits and things like that. And but it allows us to get a pretty rich things of binaries and potential binaries that have short periods.
So where is this catalog? Where can it be found?
Yeah, you're talking. Rachel Freed, is president of the Institute for Student Astronomical Research. So she has her finger on all sorts of contacts and resources, and we've got 4 or 5 people from the kind of a speckle crowd here.
Right.
So you can contact us.
I would say also as a starting point, maybe especially when you're first starting, the Washington Double Star database has, all this, essentially every double star ever, reported. So, and so it would have a lot of well-observed stars, doubles, and they would probably be good ones to start with just because they're a good sanity check to see if, any data you get makes sense against the WDS and the orbits that, that are generated from it. Yeah, the 6th orbit catalog is one that I sort of did, well, I was sort of in charge of most of my time at the Naval Observatory. And the Washington Double Star database, that goes back, that's this ancient database that goes actually back to Burnham's time in the 1870s. So it's about one of the oldest astronomical catalogs in the world right now that's still maintained. And it would be a great source for known doubles to be able to start with, I think, before you try ones that are not well observed. Yeah.
We found a calibration list of calibration, quote unquote, stars, that maybe 24 stars.
Okay.
And we've done a few of those. I say I took the picture, Doug processed the results, and we got really good results. I mean, they were right in there.
Okay, good.
But it was not using speckle. I mean, we were just
just doing CCD, astrometry, CCD imaging and astrometry from that. The vast majority of observations of double stars, especially by amateurs and such, who are not using speckle, are using CCDs now. I mean, it's that's essentially the only way that people do observations, other than speckle or huge databases you try to glean stuff out of, like Gaia and such.
Well, I've got a my Filar micrometer, and I'm committed. I'm committed to using it once.
Wow.
I've owned it for 20 years. Doug rebuilt it for me, and we're going to use it, but a couple of times just for the hoot of it.
There was a famous double star astronomer at the Naval Observatory called Charles Worley, who he made something like 40,000 observations with a Filar micrometer of double stars. And he actually, in about 1990, he saw the data that was coming out of the Chara group, Hal McAllister's group, and gave up Filar micrometer at that point. He had a speckle camera built for the Naval Observatory, and he didn't even completely reduce and publish the last of his micrometry data. He said, this is the wave of the future, and he went to that entirely when he could have easily coasted to the end of his career, using the old technique. Actually, my colleague Brian Mason at the Naval Observatory, he published Charles's last data after Charles died, like 3 days before his retirement, unfortunately. But so he was just about the last of the Filar micrometrists out there with the great double star eye, who could see closer binaries than anybody else could. So, in fact, he did one run with Hal, looking through the 26-inch with a Filar micrometer. Had Hal look at it, because Hal never done that technique. Looked at it and said, "Okay, what's the orientation of that double star?" And Hal looked at it, and he gave him, he said what it was, and Charles looked at it and says, "Nope, 90 degrees off." And he was very proud of being able to, one up McAllister, but then he switched to speckle.
So Bill, has anyone ever turned a spectral interferometer camera onto the small Magellanic clouds to see if you could see double stars there? I know probably only a small number, to see if the dynamics in those galaxies are similar to what we see here in terms of proportions and things, because technically they're classified as barred spirals. So,
right. I think there have been a handful of observations done with Magellanic clouds. Of course, with their distance, any binaries that are going to be resolved by speckle are going to be extremely wide binaries physically. And I probably no way really to tell whether they're physical or whether they're just line of sight binaries. So you can't really follow up and see the motions of them, with those kind of separations. So yeah, I don't think there's been too much out of other galaxies. There are enough double stars in my galaxy. I don't need to worry about other galaxies. I'm sorry. I don't know. It's provincial, I suppose, right?
Yes.
Bill, can I ask a question?
Sure.
Bob Buckheim, we met long ago. You pointed out that the speckle processing is best for simple targets, like 2 stars.
Right.
I know I've seen speckle results that showed a 3rd star in the system.
Oh, yes. Yeah.
And are there artifacts or things that we ought to worry about when we see that before we get all excited about the 3rd star or 4th?
We have done some observations of triples and quadruples and such, which makes a really interesting reduction patterns, because instead of the center and 2 stars, you got 5 or 6 stars for a triple, and it gets quite interesting and complicated to see them. You worry about artifacts all the time. In fact, you have electronic artifacts even with simple doubles. So the best thing to do is make more than one observation, or observe some other stars in the same field, or in the same general vicinity. And if the same artifacts kind of show up, hey, there's a double star. Hey, there's exactly the same double star for the next one. Hey, there's another double star that looks exactly the same. Then you kind of think, wait a minute, there's something else about that. So that was an issue we would occasionally have, especially observing at Mount Wilson, because as anybody who's watched through the fires going in California, they have this forest of transmission towers for all of Los Angeles are right next to Mount Wilson. So depending on which way the dome is turned, you can get quite the interesting, waves of electronic noise that can be an issue. You unshield everything as well as you can. But so when you're observing in certain parts of the sky, you got to make sure that, you're actually finding real double stars, real companions, and not artificial ones. So yeah, you always have to be on the lookout for that. Unless there's an extreme, a well-known double and you're finding it in the same spot as you expected, well, okay, you can probably be safe with that. But for discovering new binaries, you got to be real careful. So, and having published a few that were not real, I speak from experience. So I should say that one of the nice things with speckle, especially with the photographic and doing those bright stars, I can actually claim to have discovered naked eye stars, which not too many people can say. And the only reason they're not known is because they're right next to a star that's even brighter. So, but hey, they're naked eye. If that other one ever blinks out, it's there and it's mine. So anyway, that's my claim to fame, discovering bright stars.
I've got one quick question.
Sure.
This is Reed. I'm actually in my observatory.
You have a very dark background, I can see, yes.
Yeah, that's the horizon. It's cloudy tonight. The question I had, I've been experimenting with high resolution photography lately, mostly planetary. And to do this work, you're talking about more than just a standard camera, I take it. This speckle camera, it's physically different than a regular camera. It's got a double slit arrangement.
Well, the double slit mask was just to make artificial binaries for calibration on the big telescopes. With smaller telescopes, probably the simplest calibration is just looking at known doubles and doing your scale just based on well-observed binaries. So the double slits, that is not necessary. The big things that are different with speckle, essentially, now that you have CCDs that are sensitive enough, you don't need the intensifiers and all the rest of it. It's mainly optics to expand you magnify the image, right, and then be able to take the snapshots. We typically do 10 to 15 millisecond exposures, I think, for each frame, and do it at video rates. So standards.
Yeah, that's
we found
my approach.
I was just going to say that we found that the having low read noise is very nice too, and so the new CMOS cameras are allowing us to go fainter than the old CCD cameras.
Mm-hmm.
Yep, that's what I'm using now. Potentially then I could do this with my camera, but is there software to deconvolve these speckles, or is that in the realm of the professional? Has there any amateur software that people are using to do that?
Well, I think, Russ, you've probably got reduction software that your students and all have developed, right? And
yes, yeah, and
got out there.
In the classes, it was developed by Dave Rowe too. It's called a speckle toolbox, and you can do kind of regular speckle, autocorrelation, or you can do by spectrum analysis, and it's quite quite friendly and works great.
Okay.
Yes, I've heard that on YouTube. I think I can send you a reference or put that out on email.
Okay. Yeah, I might I'd give it a shot. I've got right now I'm using an eyepiece projection rig to get the magnification, you know, it's an 8-inch reflector, but it's a pretty good one. And I'm getting fairly high resolution with planetary and whatnot, so I may try it. I've heard of this, but I've never done it.
Okay, sure. Yeah, give it a try. You know, what do you have to lose? I mean, photons are cheap.
Yep.
You know.
Yep. And I am using one of the cameras he's talking about, the low noise. They're great.
Right. Mm-hmm.
Yes, photons are
cheap, but catching them's not.
That's right. I was going to say the equipment can be
yes.
very expensive.
It's gotten cheap. It's gotten a lot cheaper over the years.
Got a lot cheaper, right?
Yes.
That's true.
Yeah, it's slippery slope.
Yes. Oh, yeah. Well, it's like aperture NV. It all kind of is the same type thing. So, yeah.
All right. Do we have more questions for our speaker?
Great program.
Absolutely. It's great. And we've got guests from all over the country with us.
Oh, yeah, that's wonderful.
So we appreciate everybody being with us for the meeting.
I brought in ringers or whatever to kind of, you know,
Yeah.
pepper the crowd here.
Thanks, everybody.
Yeah, appreciate everybody for participating tonight.
Thanks for staying awake.
Oh, yeah. Okay, well, we will wrap things up. Again, thank you, Bill, for presenting. This was very, very good to have somebody from outside of Arkansas present, and somebody who has done what you've done, and we're glad to have guests from outside the state as well. So thank you, and we'll distribute some information and have the meeting up on YouTube also. So thanks, everybody, and good night.